So welcome back. In this lecture, we will continue our study of Boolean algebra. In the previous lecture, we have seen x. What happens to x and 0, x and 1, and x or 0, x or 1. So now we will go through some important identities that help simplify logical expressions. So let us start with this existence of complement. Wait for a minute. A complement represents, here it is represented as x dash, x dash. A complement represents the opposite value of Boolean variable. If a variable x has a value of 1, then its complement x prime can be pronounced as x dash, or represented as x dash, x bar, or x prime as a value of 0. Similarly, if x equals 0, then x prime equals 1. So one of the most fundamental complement identity is x plus x prime equals 1. So instead of saying it as R, so in the Boolean algebra, so for our convenience, so we are pronouncing R symbol as plus. So kindly follow this pronunciation rules to understand this lecture. So I will be pronouncing R symbol as plus and symbol as dot. So x plus x prime equals 1. This means that either the variable or its complementary must always be true. So since one of them will certainly have a value of 1, the result of our operation becomes 1. So x plus x prime is equal to 1. Another important identity is x prime x multiplied by x prime equals 0. So here in the identity number x7, x plus x prime should be 1. So here instead of mentioning as 1, it is mentioned as x. So kindly change it. In this case, that is x multiplied by x prime equals to 0, a variable and its complement can never be 1 simultaneously. Therefore, the AND operation always produces 0. We have also have in idempotent laws x plus x equal to x and x multiplied by x equal to x. So these identities include that repeating the same variable does not change the result. For example, ORing a with itself still gives a, and ANDing a with itself also gives a. So these laws play a major role in reducing redundant terms while simplifying logic expressions. So whenever repeated variables appear in a circuit design, these identities allow us to remove unnecessary gate operations and achieve a more efficient implementation. Now let us examine the commutative property. The commutative property states that the order of variable doesn't affect the result of logical operation. So for OR operation, x plus y equal to y plus x, and for AND operation, xy equal to yx. Consider two variables a and y. If a equals 1, then b equals 0, then a plus b equals 1. Similarly, b plus a also equals 1. So the result remains unchanged. This property may appear simple, but it provides greater flexibility while rearranging Boolean expressions. So during circuit simplification, engineers frequently reorder terms to identify patterns and apply other identities more easily. The commutative property allows us to organize expressions without changing logical behavior, making algebraic manipulation much more convenient. Now let us discuss the associative property. This property states that when multiple variables are connected through the same operation, the grouping of variables doesn't affect the results. So for our operations, x plus in bracket y plus z equal to x plus y in bracket plus z. So for our operation, it is like this. And for an AND operation, x bracket y z equal to xy bracket z. So imagine three input signals entering a digital system. When we combine the first two signals and then the third, or combine the last two signals and first and final results remains the identical. So the associative property is especially useful when dealing with long expressions involving many variables. It allows designers to regroup terms and simplify calculations step by step. This becomes increasingly important in large-scale digital circuits where hundreds or even thousands of Boolean expressions must be optimized. The distributive property is one of the most powerful tools in Boolean algebra. The first form is x bracket y plus z equal to xy plus xz. So this resembles the distributive law used in conventional algebra. For example, a bracket b plus c can be expanded as ab plus ac. So the second distributive form is unique to Boolean algebra. X plus yz equal to x plus y bracket into x plus z. So this identity allows us to factor expressions as well as expand them. So in practical circuit design, engineers often switch between expanded and factoral forms to determine which implementation requires fewer logic gates. Using distributive laws effectively can significantly reduce hardware complexity, resulting in faster circuits and lower manufacturing costs. One of the most important concepts in Boolean algebra is De Morgan's theorem. This theorem provides a method to simplify complemented expressions. The first theorem states the complement of an OR operation equals to the AND of complements. So mathematically, a plus b the whole bar equal to a bar b bar. So x plus y the whole bar equal to x bar y bar. The second term or second theorem states the complement of an AND operation equals to the OR of complements. That is, ab the whole bar equal to a bar plus b bar. Xy the whole bar equal to x bar plus y bar. Notice what happens. The operation changes from OR to AND or from AND to OR, and every variable receives a complement. So these theorems are very much useful for reducing the complexity. So thank you. We'll continue in the next lecture.